Okay, this is a new topic, torsional vibration. A shaft assumed to be weightless and fixed at one end and carrying a heavy disc or a flywheel at the free end can be made to vibrate in a circle about the axis of the shaft by applying an external torque on the disc. So you can see this is the shaft. So the length of the shaft is L, and then this is the disc or the flywheel. So you can see the direction of rotation is clockwise. You can see letter T here, the same thing. You can also see letter T. You have at the horizontal axis here, we have the mean position. Okay, so this angle theta is the displacement after an initial torque has been applied to it. So that is the initial displacement. So now you can see this line at an angle of theta. It is at a position after time t. Okay, so now the axis of the shaft, by applying an external torque on the disc, so in bracket, the external torque is removed after an initial displacement. So the shaft is twisted and untwisted alternately, and shear stresses are induced. So these vibrations is what we call torsional vibration. So now, example, we have been given I as the mass moment of inertia of the disc. Okay, so you can see this is the disc. Mk, and is given by I equals mk squared, where the m is the mass of the disc, k is the radius of gyration, theta is the angular displacement of the disc from its main position. You can see theta, while q is the torsional stiffness of the shaft. So the question is now, we are expected to show that the natural frequency of free torsional vibration is given by f subscript n equals 1 over 2 pi square root of q over I. So we are expected to prove this. Okay, so now the proving starts from here. Natural frequency of free torsional vibration. So the figure below, which is this figure, shows a shaft of negligible mass whose upper end is fixed, so this place is fixed, and the lower end carries a heavy disc, so this is a heavy disc. If the disc is given a twist about its vertical axis, of course this is the vertical axis, and then released, it will start oscillating about the axis, which is known as torsional vibration. Okay, so now I is the mass moment of inertia of the disc and is given by mk square. M is the mass of the disc. K is the radius of gyration in meters, so K can also be denoted with R. Theta is the angular displacement of the disc from its main position after time t, while Q is the torsional stiffness of the shaft, or the torque required to twist the shaft through 1 radian. Okay, so now the proving still continues. At any instant, the torque acting on the disc we have two torques. The first torque is the initial torque, while the second torque is the restoring torque or the spring torque. Okay, so now the initial torque is equal to the accelerating torque, but it is opposite in direction. Okay, so what's the formula for initial torque? Initial torque is given by moment of inertia multiplied by angular acceleration. So the moment of inertia is I, the angular of acceleration is given by alpha. So but you need to take note that we've been told that the initial torque is equal to the accelerating torque, but opposite in direction. So this opposite in direction means that the acceleration torque is going to be negative, and that's what you can see here. So we have I multiplied by the square theta dt squared. So this the square theta dt squared is the same thing as alpha, and that's your acceleration, angular acceleration. So now therefore initial torque, we've established that initial torque is equals to the acceleration torque, but in opposite direction. That means it's going to be minus acceleration torque equals minus I multiplied by the square theta over dt square. So now that's it for initial torque. Now to the second torque, which is the restoring torque. So the restoring torque is given by minus torsional stiffness multiplied by the angular displacement in radians. So why do we have minus here? We have a minus because it's used as a restoring torque that acts opposite to the angular displacement. Of course, it means that as a torque is applied in this direction, the restoring torque will tend to pull the disc backward in the opposite direction, and that's why it is called the restoring torque, which acts opposite to the angular displacement, and it is given by minus q multiplied by theta. So that's the formula for finding the restoring torque, minus q multiplied by theta. Now for equilibrium, the sum of all the torques acting on the disc must be 0. And how many torques have we talked about? We have talked about the restoring torque. We have also talked about the initial torque. So for equilibrium, all the sum of the torques must be 0. So this is the first torque. This is the second torque. So everything must be equal to 0. Okay, so you have negative here, you have negative here. If you multiply through by negative, everything becomes plus, and that makes it I the square theta over dt square plus q theta, everything equals to 0. So you can see that this formula is very similar to this formula when we were talking about free vibrations. Okay, so take note. So now, but now that we are talking about torsional vibration, we have it as this. Okay, so this equation 1. This equation 1. So when you divide both sides by I, we now have d square theta over dt square plus q over I multiplied by theta. Everything equals 0. Okay, now this is the fundamental equation for simple harmonic motion, which is equation 2. The square theta dt square plus omega square theta equals 0. So now comparing equation 1 and 2, okay, comparing this side, we have omega square theta is going to be equals to q over I theta. So theta will cancel theta. So that means we are left with omega square equals q over I. So omega now becomes square root of q over I. So omega is the angular velocity of the simple harmonic motion. This is also known as the natural angular velocity of torsional vibration, and is represented by omega n. So now omega n is square root of q over I, while the time period is given by t subscript p equals 2 pi over omega n. So time period of oscillation is given by this. So which is also the same thing as 2 pi square root of I over q. Okay, so this is just simple mathematics. Now the natural frequency of free torsional vibration, automatic, we already know is as Fn equals 1 over time period of oscillation. But since we already have our time period of oscillation as this, so that means we now have 1 over 2 pi square root of q over I. And this has answered this question. We are told that we are expected to show that f subscript n is 1 over 2 pi square root of q over I. And that's what we have got to here. Okay? Okay, now q, the value of q, which is torsional stiffness, is obtained from the torsional equation T over J equals C theta over L. So now theta comes here, J goes there. It means T over theta equals CJ over L. This is the simple mathematics. So now T over theta is the torque per unit angular twist and is given by Q. So automatically your Q is CJ over L. So where C is the modulus of rigidity of the shaft material, J is the polar moment of inertia of the shaft, which is pi over 32 d raised to power 4. This is the diameter of the shaft, and the L is the length of the shaft. shaft. Now we've been given an example here. A vertical shaft is fixed at the top and carries a flywheel of weight 500 Newton, 5000 Newton, welded at its bottom. The diameter of the shaft is 100 mm and its length is 1 meter. So the modulus of rigidity of the material of the shaft is 8.16 exponential 4 Newton per millimeter square. If the radius of gyration of the flywheel is 250 mm, then determine the frequency of torsional vibration. Of course, you know we are going to use the formula we just derived here. Okay, we are going to use this particular formula. So now, the weight W is 5000 Newton. We are trying to write out the data. M is the same thing as W over G. You know your weight is mg. So that becomes 5000 over 9.81 kilogram. Okay, so we have converted it to kilogram. Now we have been given the diameter of the shaft as 100 mm, which is the same thing as 0.1 meter and has a length of 1 meter. We've been given the modulus of rigidity of the material as 8.16 exponential 4 Newton per millimeter square. So now in converting it to meter to Newton per meter square, we're going to have 8.16 exponential 4 multiplied by 1 million. So everything now becomes 8.16 exponential 10 Newton per meter square, and that is the modulus of rigidity of the material of the shaft. Now the radius of gyration, which is 250 mm, is the same thing as 0.25 meters. So now this is the formula for finding the frequency for torsional vibration, and that's equation 1. Okay, so before we be able to use the formula, we need to know the value of Q. And we already established that Q from this place. We already established that Q is CJ over L, and that's what we are using here. Q is CJ over L. Okay, so now what is C? C is 8.16 exponential 10. And what is J? J is pi over 32 multiplied by D raised to power 4. So now, there's a calculation here. We know that our D is 0.1. So by the time you apply 0.1 into D, we are going to have a value for the polar moment of inertia here. So what is L? From the question, L is 1 meter. Okay, so now, eventually we now have this 0.1 raised to power 4. Everything is over 1. So by the time you simplify this further, we are going to eventually have our Q to be 8.011 multiplied by 10 raised to power 5 Newton meter. Also, your I is given by a mass moment of inertia of the shaft, which is mk squared. So now mass is 5000 over 9.81 multiplied by 0.25 all squared. So that gives us 31.855 kilogram meter square, and that is the mass moment of inertia. So now that we've gotten the mass moment of inertia I, we have also gotten Q. We can now substitute this value into the formula for frequency of torsional vibration. So Fn equals 1 over 2 pi square root of Q, which we've gotten as this 8.011 multiplied by 10 raised to power 5 over 31.855, which is our I, and eventually the frequency gives us 25.25 cycles per second, or 25.225